You ever try to slide like a really heavy bookshelf across a carpet
Mm.
and it just feels stuck, glued down almost?
Yeah.
Or the opposite, you step onto a super polished floor, maybe it's a bit wet, and whoosh, your foot just goes.
Uh-huh. Happens fast.
What are those invisible forces, that are constantly working around us, making things move or maybe stopping them from moving?
That's what we're digging into today. Friction.
Welcome to the deep dive. This is where we take your sources, unpack them, and turn them into, hopefully, some powerful insights. And today, we're doing a deep dive into friction. It seems simple, but it's surprisingly complex.
It really is.
We're drawing on some detailed engineering texts here, so we want to give you that solid foundation, really get a handle on this force.
Our mission basically is to look under the hood, see how friction works in things you use every day, your car brakes, for instance, or even just the screws holding furniture together.
Right. Prepare for a few of those aha moments about something you probably interact with constantly without even thinking about it.
It's everywhere, isn't it? But, like you said, often misunderstood. So, our sources define friction pretty clearly. It's the force that resists motion between two surfaces touching each other.
Resist motion.
Imagine them trying to slide past one another. Friction pushes back directly against that movement, always parallel to the surface where they touch.
And we're focusing today specifically on dry friction, is that right? What's special about that?
Exactly, dry friction. Sometimes you'll hear it called Coulomb friction, named after Charles Augustin de Coulomb, who did a lot of early work on it.
Oh, okay.
It just means there's no liquid lubricant like oil or grease between the surfaces. Think your bike's brake pads on the wheel rim or, a box sliding on the floor. There are other kinds, like fluid friction, but dried friction is really fundamental for mechanics.
So when engineers talk about a rough surface,
Mm-hmm.
it's not just about how it looks or feels rough to us, is it? What's actually going on down there, microscopically?
Right. If you could zoom way in, incredibly close, even something that looks mirror smooth is actually, well, jagged, full of tiny little peaks and valleys, microscopic mountains almost.
Okay.
So when you put two surfaces together, these tiny bumps, these irregularities, they kind of mesh together, they interlock.
Ah, I see.
And when you try to slide one surface, those little bumps literally catch on each other. That's the resistance. At every single tiny contact point, you get forces pushing back. Add them all up, and you get the overall friction force opposing the slide, and also the normal force pushing the surfaces together.
So it's not just like one smooth force, it's the sum of millions of these tiny little physical catches and pushes.
Precisely, yeah. Engineers, simplify this. We represent the combined effect as one resultant normal force, we call it N, and one frictional force, F.
N and F, got it.
And what's really interesting is that the normal force N, it doesn't always push right through the center of the object. Where it acts is super important.
Why is that?
Because that determines whether an object might tip over before it even starts sliding.
Oh, right, like trying to push a tall, skinny filing cabinet.
Exactly. If you push it too high up, you create this turning effect, a tipping moment. To stop it from falling over, the cabinet's own weight has to create an opposing moment. And it does that by shifting where that effective normal force N is pushing up from the floor. It's all a balancing act.
So it's this constant question, will it slide first or will it just tip?
That's often the core problem, yes. Where does N effectively act? That dictates the stability.
I saw something else in our sources. It mentioned friction isn't just about the physical bumps. It can involve temperature, material density, even how clean the surfaces are, or atomic attraction. That sounds way more complicated.
It absolutely is. The classical model we're focusing on, the Coulomb model, it works incredibly well for most engineering situations. But if you really dive deep into the science of it, that's called tribology, the study of friction, wear, and lubrication.
Tribology.
Then yes, all those other factors start to play a significant role. Temperature can change material properties. Surface films matter. But for designing bridges or machines, the macroscopic dry friction models are usually robust enough. Powerful tools.
Okay, let's get into something you mentioned earlier, this idea of impending motion.
Yeah.
What exactly does that mean? How's it different from, actual moving?
Right, impending motion. Think about that heavy bookshelf again. You start pushing it just a little bit.
Okay.
Friction pushes back with the exact same force, equal and opposite. So nothing moves, it's static. Now you push a little harder.
Friction pushes back harder too.
Exactly. It matches your push perfectly, keeping everything still, but it can only do that up to a certain point. There's a maximum value it can reach.
Ah, the limit.
The limit. We call that the limiting static frictional force, usually written as Fs. Right at that point, the bookshelf is like trembling on the verge of moving. It's perfectly balanced but unstable. Any tiny bit more force.
And it starts to slide. So that's the threshold, that
Yeah.
split second just before movement.
Precisely. That's impending motion.
Is there a way engineers calculate that maximum static force, Fs?
Yes, absolutely. This is probably the most fundamental equation in dry friction. S equals sines nm.
Fs equals S? Okay, break that down.
S is that maximum static friction force we just talked about. N is the normal force, basically, how hard the surfaces are squished together. More weight means more potential static friction.
Makes sense.
And S, that's the key. It's called the coefficient of static friction.
Dievos.
Forces is a number. It doesn't have units, and it basically quantifies how grabby or sticky those two specific surfaces are before they slip. It depends hugely on the materials. Rubber on dry pavement has a very high ice on steel. Very, very low ions.
So engineers need tables or experiments to find the right ions for their materials.
Exactly. It's usually determined empirically through testing. Very important value for design.
Okay, so Owens tells you the resistance before sliding starts. What happens once you overcome Fs and it does start moving? Does the friction stay that high?
No. And this is really crucial, one of those aha moments you mentioned. As soon as your push force, let's call it P, gets just a tiny bit bigger than F's, the object starts sliding. And the moment it does, the friction force actually drops.
It drops. To what?
It drops to a lower, generally pretty constant value. We call this the kinetic frictional force, FK. And it's almost always less than the maximum static friction Fs. Often it's maybe, say, 25% lower, roughly.
So there's an equivalent equation like FKKANN.
You got it. Fk is a coefficient of kinetic friction. And just like we said, F is typically smaller than S.
That explains so much. That's why it's always harder to start pushing something heavy than it is to keep it sliding once it's moving.
Exactly that. Think about trying to push a stalled car. That first budge is the real effort. Once it's rolling, even really slowly, it feels noticeably easier, right?
Totally.
Our sources show this really well with graphs. Friction force ramps up linearly with your push, hits that peak Fs, then bam, drops down to frac as soon as motion begins and stays pretty much level after that. It's a critical difference engineers always have to account for.
That makes perfect sense now. Okay, so knowing all this static versus kinetic, einkommen und Technics, tipping, how do engineers actually tackle problems with friction? It feels like there are a lot of possibilities. Will it slip? Will it tip? Will it just stay put?
It can definitely seem tricky, but engineers have developed systematic ways to approach it. Think of it like being a detective. There are usually three main types of static friction problems, and the first step is always the same. Draw a clear free body diagram.
The diagram showing all the forces acting on the object.
Precisely. You need to visualize everything, the weight, applied forces, the normal force, and the friction force. Then you figure out which case you're dealing with.
Okay, what's the first case?
The first type is when there's no apparent impending motion. Basically, you don't know for sure if it's about to slip or not. Maybe it's perfectly stable.
So you assume it's stable.
You start there. You write your equilibrium equations. Sum of forces equals 0. Sum of moments equals 0, treating the friction force F as just another unknown variable you need to solve for.
Okay.
Once you solve the equations and find the value of F required to keep things in balance, you then have to check it. Is this required F less than or equal to the maximum possible static friction, Sn?
The reality check.
Exactly. If F is less than or equal to Sn, then your assumption was correct. Equilibrium holds, it doesn't slip. But if your calculated F turns out to be greater than Sn,
then it can't actually provide that much friction.
Right. It means your initial assumption was wrong, the surfaces can't provide that much resistance, and slipping will occur, so you then have to reevaluate using kinetic friction.
Okay, so verify if the surfaces can handle the load. What's the second scenario?
The second type is when you know impending motion occurs at all points of contact. The problem might state it directly, like, find the force needed to just start the block moving.
So slipping is guaranteed to be about to happen.
Yes. In this case, you don't treat F as an unknown. You use the full static friction equation right away. F Fs equals SSN at every point where slipping is impending. You plug that relationship directly into your equilibrium equations.
Ah, so that gives you an extra piece of known information.
Exactly. It usually gives you enough equations to solve for all the unknowns, like the applied force P needed to reach that tipping point, or maybe an unknown angle.
Makes sense. And the third type? I'm guessing that's the most complex one.
It often is. That's when you have impending motion at some points. Or maybe you just don't know what will happen first. Will it slip at point A or point B? Or will the whole thing tip over instead?
Right, the slip or tip dilemma.
Yeah. Here you often have more unknowns than standard equilibrium equations, plus the simple F is S is N can handle. So the strategy is to consider different possibilities as separate cases.
Like different hypotheses.
Kind of. You'd hypothesize. Case 1. Assume it slips at point A first. Calculate the force P needed for that using Fa equals twice S and A. Case 2. Assume it tips instead. Calculate the force P needed for that, which usually involves moments. Case 3. Maybe assume it slips at point B, if there is one. Calculate P for that.
And then?
And then you compare the forces you calculated for each case. The smallest calculated force tells you what actually happens first in reality. If the tipping force is smallest, it tips before it slips. If the slipping force at A is smallest, it slips at A first. It's a process of elimination to find the true failure mode.
That's clever. Systematically checking all the ways it could fail or start moving. What about the direction of that friction force, F? How important is getting that right on the diagram?
Oh, critically important. Friction always opposes the motion, or the impending motion. So when you're using F, S as N because you know slipping is about to happen, you must draw F, pointing in the direction that opposes the way it's trying to slide.
Yeah.
Because that equation F equates Sn only gives you the magnitude, the size of the force. The direction comes from understanding the physics of the situation. Now, if you're in that first case, no apparent motion, where F is just an unknown,
Yeah.
you might have to make an initial guess about its direction on your diagram. If you solve the equations and your calculated value for F comes out negative, it just means you guessed the wrong direction initially.
So you just flip the arrow on your diagram.
Exactly. The math tells you reality. A negative sign just means it acts opposite to your assumption.
Okay, that clarifies the analysis part.
Yeah.
So once engineers can predict friction, they can start using it deliberately, right? Engineering with friction, not just against it.
Absolutely. Now we get to the applications, where friction is the hero, not the villain.
What are some classic examples?
Well, one of the simplest yet incredibly effective is the wedge. Like for splitting logs or jamming under a door to hold it open. Wedges are amazing tools. They take a relatively small force applied to their end and translate it into much, much larger forces pushing outwards, perpendicular to the wedge faces. Friction is key here. It acts along the sliding surfaces of the wedge, opposing its motion.
And I've heard of wedges being self-locking. What does that mean?
Good point. Self-locking means that once you push the wedge in, maybe hammer it into place, and then you remove the force you were applying, it just stays there. It doesn't pop back out on its own.
Why not?
Because the friction forces along its sides are large enough compared to the angle of the wedge to completely counteract the forces trying to push it back out. The steeper the wedge angle, the less likely it is to be self-locking. A very shallow angle wedge with enough friction will hold tight, super useful for adjustments or temporary fixtures.
From wedges holding doors to something even more common, screws. They literally hold our world together. How is friction working there?
Screws are ingenious, especially things like square-threaded screws you find in vices or car jacks. You can think of a screw thread as basically an inclined plane, like a ramp wrapped around a cylinder.
Ah, okay. I could visualize that.
When you turn the screw, apply a moment or torque, you're essentially pushing a load up or down this helical ramp, and friction acts all along the surface of that thread, resisting the turning motion.
So the turning force fights friction.
Yes, but here's the magic. That relatively small turning force you apply gets magnified into a huge axial force, a force acting straight along the length of the screw. Think about lifting a car with a jack. You turn the handle with moderate effort.
And it lists thousands of pounds.
Exactly. That's mechanical advantage, amplified by the screw's geometry, and importantly, controlled by friction.
And screws can be self-locking too, right? Like the car jack example.
Yes, very often they're designed to be. The screw is self-locking if, when you stop turning the handle, the weight of the car doesn't just cause the screw to unwind itself backwards.
What makes it self-locking?
It happens when the angle of the thread, the ramped angle, is shallow enough, and the coefficient of friction between the threads is high enough. Basically, the friction-resisting unwinding is greater than the tendency of the load to slide back down the ramp. If it wasn't self-locking, you'd have to constantly apply a holding force to the handle just to keep the car up.
That would be inconvenient.
Very. Engineers can calculate the exact moment needed to raise a load, overcoming friction, or lower a load where friction might actually help unwinding, or you might need to apply a reverse moment if it's self-locking and you want it to go down. But the key is that force amplification and the self-locking potential, all thanks to friction.
Okay, let's shift gears slightly. What about belts? Like conveyor belts or the serpentine belt in a car engine? Friction seems crucial there too.
Absolutely crucial. Belts are fantastic for transmitting power or motion between rotating shafts, pulleys, or drums. The whole principle relies on the friction developed between the belt material and the curved surface it wraps around.
So the belt grips the pulley because of friction.
Precisely. And here's what's really powerful. The relationship between the tension in the belt on the tight side, pulling the load, and the tension on the slack side, returning, is exponential.
Exponential. How so?
It means that even with a fairly small coefficient of friction, if the belt wraps around a good portion of the pulley, what we call the angle of contact, the difference in tension between the tight side, T2, and the slack side, T1, can become enormous. The formula is T2 equals T1E, or is the friction coefficient, and this is the contact angle in radians.
Wow, so a little bit of friction and enough wrap angle lets you transmit a huge amount of force.
Exactly. That exponential factor can get very large quickly. A small pull on the slack side, T1, can allow the tight side, T2, to exert a massive pull.
Does the size of the pulley matter, like the diameter?
Interestingly, no. Not for the tension ratio itself. Look at the equation. T2 equals T1E. It only depends on the coefficient of friction and the angle of wrap-up. The radius of the drum or pulley doesn't appear in that core relationship.
That's surprising. So the same principle applies to a tiny pulley or a giant industrial drum.
For the tension ratio, yes. Of course, the torque transmitted will depend on the radius, torque T2, T1 radius, but the fundamental gripping capability due to friction depends only on liability. It's another elegant principle engineers leverage constantly.
Very cool. Okay, staying with rotation, what about things like shafts rotating in bearings, especially where maybe lubrication isn't perfect, so dry friction is relevant?
Right. Bearings are essential, but when we're talking about situations closer to dry or poorly lubricated contact, like maybe a simple journal bearing, which is essentially just a shaft rotating inside a slightly larger hole, friction causes an interesting effect. As the shaft starts to turn, it doesn't just spin perfectly centered in the hole. Because of friction between the shaft surface and the bearing surface, the shaft actually tries to sort of climb up the wall of the bearing in the direction of rotation.
It climbs.
Just a tiny bit, until it reaches an equilibrium point where it's just on the verge of slipping. The actual contact point shifts slightly from the very bottom. This creates what engineers call the friction circle.
A friction circle. What is that?
Imagine drawing a very small circle around the center of the shaft's cross-section. The resultant force from the bearing, which is composed of the normal force and the friction force, always acts tangent to this tiny circle. The radius of this friction circle is approximately equal to the shaft's radius times the coefficient of kinetic friction, RFARK, because it's sliding.
Okay. So why is this friction circle useful?
It helps visualize and calculate the small amount of torque or moment that's required just to overcome the bearing friction and keep the shaft rotating at a constant speed. That moment is basically the load on the shaft multiplied by the radius of that tiny friction circle. It represents the energy loss due to friction in the bearing.
So to minimize friction and wear in these simple bearings, you'd want a small shaft radius or obviously a very low coefficient of friction.
Exactly. Keep that friction circle as small as possible, which is precisely why, in practice, for anything demanding efficiency or longevity, designers move away from simple journal bearings towards things like ball bearings or roller bearings.
Because they rely on a different principle.
Precisely. They introduce our final key concept, rolling resistance.
Right. Rolling resistance. This feels fundamental. Why is it so much easier to roll something heavy, like on wheels, than it is to just slide it? We know it is, but what's the physics?
It really comes down to deformation. Even seemingly rigid objects like a steel wheel on a steel rail or, more obviously, a rubber tire on pavement deform slightly where they contact.
Okay, they squish a little bit.
Just a tiny bit. Now, as the wheel rolls forward, the material in front of the contact point gets compressed. It sort of bunches up, creating a tiny hill that the wheel constantly has to roll up and over.
Microscopic hill.
Microscopic, yes. but real. Meanwhile, the material behind the contact point is springing back up as the pressure is removed, but it doesn't push the wheel forward effectively. The net result is that the supporting force from the ground, the normal force, doesn't push straight up through the center of the wheel's axle anymore.
Where does it push?
It shifts slightly forward by a very small horizontal distance. Let's call that distance B.
Ah, so there's an offset now.
Exactly. And to keep the wheel rolling at a constant speed, you need to apply a small horizontal force, P, that creates a moment to counteract the moment caused by the load W acting through that offset distance B. Basically, P times the wheel radius R has to balance W times the offset B.
So P is proportional to that tiny offset B.
Yes. That small distance B is called the coefficient of rolling resistance. And because B is generally very, very small, much smaller than the effective lever arm involved in sliding friction, the force P needed to overcome rolling resistance is typically far less than the force needed to overcome sliding kinetic friction, FK.
That's the secret. The deformation creates a tiny resisting moment, but it's much smaller than the force needed to just drag something.
That's the essence of it. It's why the invention of the wheel and later ball and roller bearings, which replaced sliding with rolling internally, was so absolutely revolutionary. It dramatically reduces the effort needed to move things.
Wow. Okay, we have covered a lot of ground today on friction. We really did deep dive, didn't we? From those microscopic bumps causing it, hearing about Coulomb's early work, right through to how engineers predict if something will slip or tip.
Yeah, and the crucial difference between static friction, that initial stuck feeling, and kinetic friction once things are moving. Then exploring how we actually harness it cleverly in things like wedges and screws.
And belts,
Yeah.
using that exponential grip, and even understanding the subtle resistance in bearings. And, finally, why rolling is just so much more efficient than sliding.
So the big takeaway for you listening should be that friction isn't just some annoying force slowing things down. I mean, sometimes it is, but it's also absolutely critical. It's measurable, predictable, and it dictates how almost everything in our physical world moves, or indeed how it stays put.
Right. From that delicate balance right before something slips, that impending motion, to the incredible leverage you get from a simple screw thread. Understanding friction really means you're understanding a core principle of engineering and physics.
It governs so much.
So here's something to think about next time you're just, say, walking across the room or maybe tightening a screw or even just watching a car brake at a light. Consider this. What tiny, subtle changes might be happening right then? Changes in the surface, maybe the material, maybe even the temperature?
Yeah.
How are those continuously altering that invisible coefficients of friction? And how do engineers design things to account for those constant, tiny, unseen variations in the forces that hold our built world together?